Okay, so let's take it away. So greetings, everyone. It's My name is Derek Abbott, and it's a pleasure here today at Adelaide University's Algebra Workshop 2026, and it's my great pleasure to introduce our guest speaker, Ruvi Lakamosam, from who's a scientist at the A-Star Institute in Singapore, but is originally here from Australia. He's Australian, and he did his PhD in physics at ANU. Um, I'm looking very forward to this talk. Ruvi, please take it away.
Hi, Derek. Nice to be here. Thanks for inviting me. So, I'm going to be talking about a few different topics within this area of how you can use abstract mathematical ideas like Lie algebra and geometry to try and understand and solve the dynamics of quantum systems. So, I'm based at the A-Star Quantum Innovation Center in Singapore. So, this is basically Singapore's version of CSIRO, a government research lab. So, we do a lot of work in quantum optics, quantum sensing, quantum materials, trying to use quantum systems to build new technologies. So what I'm going to talk about is firstly, some work I did with, firstly, we'll give an introduction on how you can use Lie algebras to understand dynamics. Then I'm going to talk about a Mathematica package, operator algebra, that I did together with my old PhD supervisor, Joe Hope, that can do a lot of Lie algebra calculations automatically. Then some work on how Lie algebras can help you understand problems in quantum sensing. That was done with Tanya and Jason at the Okinawa Institute of Science and Technology in Japan. And lastly, I'll talk about, I call it real Lagrangian mechanics. It's how you can really truly free yourself from the constraints of Euclidean space and developed Lagrangian mechanics with total freedom, the way it's meant to be. And that was done with Chen Ye Ang. I couldn't get a picture of him in time, so I have just duplicated Joe's picture there. So let's start off with Lie algebras and dynamics. Here's a question. How do we describe the orientation of a spherical pendulum? So we've got this rigid rod and we've got a ball on the end, and you can imagine this ball can move all around the sphere. As it goes, it can not only move, it can also twist and turn. So it's got the full rotational degrees of freedom. One way of doing this is what's called Euler angles. So we use three different angles as shown here. And once you know those three angles, you can completely describe the orientation of this sphere. So how do we actually find equations of motion? We can do some trigonometry, and we can convert these three angles into an x, a y, and a z position. So x, y, and z just depend on theta and phi. This angle psi just controls the rotation of the sphere. Now, once you've done that, you can write down a Lagrangian. So your kinetic energy, you have this translational component, and you have this rotational component. And you have your gravitational potential energy. So you take your x, y, and z, and you substitute them in terms of theta, phi, and psi, like we've got here. And then you use these Euler-Lagrange equations. And with this, you can get equations of motion for this pendulum in terms of just these three angles. Now, this is all very well and good. So let's say you do this and you code up some sort of numerical simulation. So you have this pendulum and it's moving and swinging and turning all around this sphere when suddenly something terrible happens. What happens if this sphere just happens to twist and turn and reach the South Pole? Why is this so terrible? If you look on the left-hand side, we've got these three angles here, and this pendulum has 3 degrees of freedom. It can move in 3 dimensions. With this blue, it can move this way. With the orange one, it can move up and down. And with this psi angle, it can rotate. It's a 3-dimensional configuration space. But as soon as you hit the South Pole, 2 of these angles become degenerate, right? This blue angle is the angle with this x-axis, but now the angle with the x-axis coincides with psi. And suddenly at this orientation, your space becomes 2-dimensional. You can only move in 2 dimensions. Your space has lost a degree of freedom. Now, this isn't a physical problem. In reality, there is no problem with pendulums reaching the South Pole. This is a coordinate singularity, a problem with our coordinates. And if you are doing any kinds of numerical simulations, they will react violently. They might blow up and explode, or if you're doing analytics, you might have problems with that. So why does this happen? This is because the dynamics of this pendulum have a spherical topology. Now, when we write down angles theta, phi, and psi, like we in our brain, we know that these are angles. We know that theta equals 0 and theta equals 2 pi are the same. But in the actual mathematics, that's not there. The equations of motion don't know that 0 and 2 pi are the same. As far as they're concerned, theta equal to 0 and theta equal to 2 pi are two different configurations. So when you write down Euler angles, what you're doing is you're taking this rotational spherical topology and you're tearing it and you're forcing it into flat space. And this has consequences, which are there will be singularities at particular orientations. So how can we get around this? Now imagine a globe, like we've all seen maps before, a map of the world. And what a map does is you take the Earth, which is a sphere, and you somehow flatten this onto a 2D piece of paper. And if you've ever paid attention to a map, you'll notice that this always causes distortions. For example, in the most commonly used maps, the land masses at the North and South Pole get massively increased in size. So, and again, this is because you're taking something that is spherical and you're trying to map it into a flat space. So one option is, which is done in a map, which is done with Euler angles, you introduce singularities. You cut your and tear and stretch your system somewhere. But there is, in fact, another way to represent a curved space in flat Euclidean space without doing any singularities. And the clue is you look at this sphere here. Now, it is just sitting there harmlessly, no singularities at all. And the reason for that is we've taken our sphere, which is two-dimensional, and we've embedded it in three-dimensional Euclidean space. We've added a dimension. So this is another way that lets us get around the singularity. We take our curved space and we put it into a higher dimensional flat space. So let's try and do that with the pendulum. The pendulum is a three-dimensional object. It's got 3 degrees of freedom for its configuration. But what we will do is we will embed this in 9-dimensional space. And how we will do that is we'll use a rotation matrix. So imagine the sphere initially starts at the North Pole. The pendulum is initially at the North Pole of the sphere. Whatever configuration it is now, you can write down a rotation matrix that would take it from the North Pole to its current configuration. So this is a rotation matrix acting on Euclidean space. So it's a 3x3 matrix with 9 components. So that means is if you have any configuration, you can find a corresponding rotation matrix. And if you have a rotation matrix, you just apply that rotation matrix to the North Pole and you end up with a configuration. So we can actually describe the orientation of this pendulum using a rotation matrix, which is, it sounds really fancy. We are embedding the spherical topology of our pendulum into 9-dimensional Euclidean space, but it's this idea that we can just pick whatever coordinates we want. Like we as a human being, when we're solving a problem, we should have complete freedom to use whatever coordinates we want. And so what I want to say here is, let's just use a rotation matrix as our coordinates for the sphere. So now let's see how we can construct this theory. If we have said, hey, I want to describe the orientation of my sphere with a rotation matrix, how can I now go on to derive equations of motion? The first thing to do is, now I have my position, I need my velocity. So if we imagine the sphere is a two-dimensional object, and velocities are represented by the tangent plane. These are my infinitesimal directions that you can move in along the sphere. Now, even though the sphere is two-dimensional, we embed it in three-dimensional space. But the tangent plane stays two-dimensional because the tangent plane represents the directions that you can move along our sphere. So the point is, if you take your curved space and embed it in higher dimensional space, your tangent space still has the original number of dimensions. So we've taken our pendulum here, we've embedded it into nine-dimensional space using a rotation matrix, but the tangent vectors, the things representing our angular velocities, that's still going to be a three-dimensional space because there's only three dimensions that our pendulum can move in. So there is, out of these 3 by 3 matrices, there is a three-dimensional subspace representing the velocities of the pendulum. So let's try and find this. Suppose you start at the north pole of the pendulum and you twist it about the x-axis. Then your pendulum will trace this curve along the sphere. And up here, this is your infinitesimal velocity, the derivative right at the origin. So I've drawn a 2D plane here. That's just for visualization. Again, the tangent space should be three-dimensional here. So how can we find this tangent vector? So firstly, this is the rotation matrix that represents this curve along the sphere. This is a rotation about the x-axis for time or angle t. So as t changes, this will go here. So if r is our position, how do we get the velocity? Well, the velocity is the derivative of r. So we take r, we differentiate it. Okay, this represents the velocity at time t, at angle t after this has been turned. So how do we find this vector here? This is the vector when t is equal to 0. So v at 0, when we substitute t equals 0, is here. So I will call this sigma x. This is the matrix that represents a velocity here corresponding to rotation about the x-axis. Now we can do the same thing for y and z, and we end up with these three matrices here, which I will call sigma x, sigma y, and sigma z. If you have a general tangent vector, that means rotation in an arbitrary angle or about an arbitrary axis, you can express it as a sum of these vectors. So this three-dimensional subspace of matrices describes your tangent vectors at the origin. So now we started with our position, and from that we've derived our velocity. So what about the tangent vectors at other points? Because of symmetry, we can always rotate this plane back to the origin. And because of that, we only ever have to care about the tangent vectors at the origin. Because at each point on the sphere, you would have a different subspace of tangent vectors corresponding to the different locations on the sphere, which would introduce some complications. But instead, we use the symmetry of the sphere to always work at the origin plane and rotate those vectors to wherever it is right now. So now, suppose we start at the origin with tangent vector v, and we evolve for a time t. Where will we end up? Like, let's say you give me one of those matrices. How can I find out where this takes you after a time t? So at each point r, the tangent vector is vr. So what do I mean by that? Remember, v is the tangent vector at the origin, and r rotates that vector to your current location. So our differential equation is r dot equals vr. So the solution is r equals e to the vt, where this is the matrix exponential. Remember, v is a 3 by 3 matrix interpreted as a power series. So in other words, if you give me a tangent vector v, if I compute e to the vt, that will give me the rotation matrix corresponding to my orientation after rotating by angle theta about that axis. In other words, if I want to know where do I end up after rotating theta about the x-axis, I compute e to the power theta sigma x. And if I do this matrix exponential, I really will end up here. Now, here's a question. Let's say I start off at the origin and I rotate around the x-axis by some angle delta. Then I rotate around the y-axis by angle delta. And now I undo this. I rotate back around the axis by minus delta and back around the y-axis by minus delta. So I'm going in a loop. I go x, y, x, minus y. Where will I end up? Will I end up exactly how I started? So using this, we can actually compute this, because we said that e to the We have e to the delta sigma x rotates around the x-axis, e to the delta sigma y is the y-axis, then minus sigma x minus sigma y. I just look at the product of these matrix exponentials. And using the Taylor expansion, you can show that this thing is equal to e to the delta squared times this commutator, which is, sigma x, sigma y minus sigma y, sigma x, plus some higher order terms that we'll neglect. We'll assume delta is small. Now, if we actually work out this commutator, the commutator of sigma x with sigma y is sigma z. So what this is telling us is if you go around in a loop like this, it will do a small rotation about the z-axis by angle delta squared. Now, in general, the commutators between these x and y are given by this, where this epsilon is the Levi-Civita symbol. It just gives you the sign. It's saying that if you do yx, you get minus z. But this is quite interesting because now what we've got is we've got commutators showing up in classical dynamics. Whereas previously, this all looks quite quantum, right? You've got time evolution. This looks like the unitary time evolution operator. We've got what looks like the Pauli matrices here, sigma y, sigma z, sigma x, Pauli matrix commutators. And we're also seeing that the commutator shows up. It has a consequence in the dynamics. And I think this is something quite important when we try and think about fundamental theories of quantum and what quantum really is. A lot of things that we associate as features of quantum mechanics, things like commutators, are actually features of matrix mechanics. And matrices can be used to describe quantum systems, but they can also be used to describe classical systems. And it's just something I think to bear in mind, especially nowadays, that there's a lot of thought on fundamental theories of quantum. So let's summarize all this and put it in some mathematical vocabulary. We've got this system like the pendulum, and its configuration space is something called a Lie group. And what that just means is we have this set of configurations, and if we want to get from one configuration to the other, we apply some sort of rotation. Now we have to choose coordinates on this group. We could choose Euler angles. So for example, on this group, we could choose the Euler angles as we did before, or we could choose the rotation matrices. And some choices of coordinates will have singularities, but these are singularities in our coordinates. And the tangent space at the origin is called the Lie algebra. And if you have some tangent vector sigma j, you can generate a configuration by taking this matrix exponential, e to the power theta sigma j. Now, as we said before, you only have to know these tangent vectors. We call them the generators because using these vectors, you can construct and rotate with that vector to end up anywhere. We can only care about the tangent space at the origin. And if we care about somewhere else, we just rotate it back to the origin and work there. So the way that we did so far was we started off with our rotation matrix and we worked backwards to find the generators. But we can actually go the other way. We can say, hey, say I want to describe a particular configuration, first rotate about the global z-axis by angle psi, then rotate about the x-axis by angle theta, and now rotate about the z-axis by angle phi. And if you go and you work through, you'll see that it puts you in a configuration like this, where theta is the angle with the z, phi is the angle with x, and psi is this angle about here. So if you had different orderings, this theta, phi, and psi would correspond to different locations on the sphere. So the point is, once you have a list of all the generators, you can just write down this product of exponentials, and that can represent any element of our group, any possible configuration. Now, you might have a question, isn't this just Euler angles? And the answer is, this is Euler angles. This is another way of thinking about Euler angles. We have a set of generators that describe the possible rotations, and by taking a product of these, we get a general rotation matrix. So now let's make the connection to quantum mechanics. Let's suppose we have an optical cavity. So this is described by a Hamiltonian here. A and A dagger are our annihilation operators. So this term here is the cavity frequency, and this is some driving laser pumping our cavity, increasing the photon number in the cavity. We just saw in our Lie algebra, in our classical dynamics case, if you have some configuration R, our equation of motion is R dot equals VR, where V is the sum of these matrices, sigma x, sigma y, and sigma z, with scalar coefficients. And we saw that if this was the case, then we could write R as a product of these generators, a product of exponentials of generators. Now, in the quantum case, we have a unitary operator U, and U is just the complex analog of rotation matrices, U dot equals minus IHT, where H is now a sum of operators, A dagger A dagger, and A. Now, just like these sigmas were matrices, these A daggers A's, you can also think of them as matrices, as operators. And then by exactly the same kind of logic, that means our unitary operator U can be written as a product of exponentials like this. And then physicists call this the Wei-Norman expansion after this paper, Wei and Norman, where they introduced it, which I highly recommend. It was very readable. Like they wrote it in a way where people without a mathematical background could understand it. It's a very good paper. Mathematicians, they call this exponential coordinates of the second kind, just if you're ever trying to Google information about this. Now, the generators need to be closed under commutators. So what I mean is, let's say R dot, if we come back to this example, only had a x and y component. There was no z component here. So you were only moving around the x and the y-axis. But as we saw in our earlier example, just by rotating around x and y, you can create rotations about z because the commutator of x and y creates z. So even if your only have x and y in your equations of motion, when you write down this product of exponentials, you have to have every operator you can get by taking commutators of these operators. Similarly, if we look at the operators in our Hamiltonian, this product of exponentials needs to have every possible operator you can get by taking commutators of operators here. So in fact, I am missing one. So the commutator of A dagger A with A dagger is A and so on, but the commutator of A dagger and A is 1. So I should actually have an extra phase term, e to the power c4 of t times just 1. But a phase doesn't change anything in our dynamics, so we can neglect it. So when I first found out about the Wei-Norman expansion, it seemed like some kind of natural coordinates for quantum mechanics, a very geometric way of looking at things. And I was very entranced by this. I loved it. And I did everything I could to take any problem I was looking at and transform it into these coordinates to use the Wei-Norman expansion like this. And I thought that this might make things easier to solve analytically. But now, what I've realized is that these will almost always have singularities. And it's because it's fundamental. It's just like those Euler angles you see before. You end up in some particular configuration, some particular value of C1, C2, and C3. And when you hit that, you get singularities and your equations of motion blow up. So I tried for a very long time doing all kinds of things like, can you dynamically change your coordinates, change your ordering as you move to try and dodge these singularities? But it just ended up being a huge pain. So now basically, I do not like the Wei-Norman expansion. I think it's a very kind of ugly thing with like a very unnatural thing. And I hope that the intuition for this is exactly the same as the intuition here. It does have its uses. Like I'm not saying never do the Wei-Norman expansion, but I'm saying don't see it as some kind of geometric panacea that is always the right thing to do. It's a particular choice of coordinates on your system that may or may not be the right ones. Now, I'll very quickly talk about operator algebra, which is a Mathematica package. Very often, you want to work out things like commutators of operators. So here I have a list of operators. This is in an optomechanical system where we have x and p representing the momentum of some physical object, and NA, that is A dagger A, if I have some optical light field. And here I have a long list of operators, A dagger A dagger squared, XP, and so on. And all you have to do is basically tell it the individual commutators, that the commutator of x and p is I, and that x and p commute with NA, and then you can work out this full commutator table automatically and can do all kinds of other things. If you're interested, you can have a look at that QR code at the top. Now I will talk about this problem in quantum sensing that I looked at with Tanya and Jason at the Okinawa Institute of Science and Technology, where I did a postdoc for 2 years. So firstly, what is quantum sensing? Whenever we make a measurement, there is noise. It might be thermal noise from heat, it might be vibrational noise from the environment. So if it's hot, we put it in a fridge. If there's vibrations, we use some springs to isolate it from the environment. So we can go and go and go and cut out all this classical noise. But finally, we will see some kind of fundamental noise that we cannot get rid of using classical means. So this is quantum noise, and we need to look at quantum sensors based on quantum techniques to make our way through that noise. And secondly, quantum systems have things like superposition and entanglement. These are very sensitive. Can we use these quantum features to create sensitivities beyond what's possible classically? And when we look at problems like wave function collapse and quantum gravity, these are fundamental questions about quantum mechanics, and they're very small effects. We need very sensitive measurements to detect these. So it seems reasonable that we need to use quantum sensors to solve these problems. So let's talk about the kind of model for quantum sensing. Excuse me. So we start off with some kind of quantum system rho. And imagine it starts off here at the origin, and the state depends on some parameter theta. So for example, let's say we have this Hamiltonian here, and we have some normal h bar omega sigma z, some rotation about the z-axis, and some unknown rotation about the x-axis. For example, z could be the Earth's magnetic field, and there's some other fluctuation about another axis that we're trying to measure. So we let our system evolve for time t, and depending on the value of theta, we will end up at different places. Our state will end up in different states that depend on the value of theta. And the point is that we measure our system, and from the measurement results, we try and work backwards to figure out what theta is. Because for a quantum system, you can never actually see the state directly. We can measure it in some basis, and we have to work backwards to see what is the quantum state. Now, when we want to study the fundamental limits of sensitivity, there's this tool called the quantum Fisher information, and it tells us fundamentally what is the smallest fluctuation in theta we can detect. So what this says is if we do this experiment n times, if we get n of these probes and we measure them, and then we try and estimate theta, our error in theta will be greater than 1 on n, which is our number of measurements, times the quantum Fisher information. So if you have a very high Fisher information, that means your error can be very small. You can estimate theta very accurately. Now, the quantum Fisher information is defined as how different is rho of theta and rho of theta plus delta theta, where delta theta is some infinitesimal increment. And the idea behind this is if when you change theta by delta theta, your state changes a lot, then you will be able to discriminate. You'll be able to detect this change. But if your state doesn't change at all or changes very slightly, then you're not going to be able to use this to figure out what theta is. So mathematically, it's defined as the distance between rho theta and rho theta plus delta theta using something called the Buer's metric, which is just you look at all possible purifications of these two states and minimize over that. But the intuition is you just look at how different is rho theta and rho theta plus delta theta, and then this tells you your sensing accuracy. And so the quantum Fisher information is something we want to work out. It tells us with our system, fundamentally, how well can we do? How well can we measure this parameter, these fluctuations in the magnetic field or this quantum gravity signal? And it tells us like, what is the best case performance? And then you can use this to figure out, is this quantum system worth caring about? Oh yes, there's some error in my slides, but the point is, there was this paper here where they said, let's say you have unitary evolution. So you start off with some state rho, and it evolves under a unitary operator, which depends on our parameter. So rho can evolve to u theta or u theta plus delta theta. Now, let's say you want to find the quantum Fisher information of this process. They said, find your u, differentiate it, and then multiply by u dagger. You get something called v, and you work out the variance of v with respect to your initial state. This is a statistical question. It's saying if you measured v, what would be the variance in your measurement results? Now, I was very excited when I saw this, because I think, let's try to understand what v is. So here is u theta, here is u theta plus d theta. So this derivative is this vector here. And then when you multiply by u dagger, what you're doing, you're rotating backwards, the opposite rotation to u theta, back up to the North Pole. And then you're working out what is the variance of V with respect to your initial state. Now, if you look at this is very similar to all that stuff we did earlier. It's saying that the quantum Fisher information is a tangent vector that lives in the Lie algebra. And then my question was, okay, can we now use all this geometric intuition from earlier to try and study the Fisher information, maybe compute it more easily? So firstly, let's talk about how a lot of people solve this problem using the Weyne-Norman expansion, and then why we think the Lie algebra can provide another approach. So here is our Hamiltonian, and what I've written here is these xj, they're the operators in our Hamiltonian. So our Hamiltonian is a sum of these operators with scalar coefficients. So t is time, they can evolve with time, and theta is the parameter. Our Hamiltonian depends on this parameter. And we say that these xj are closed under commutators. If you take the commutator of any two xj, you get this gamma is just a matrix of coefficients, it's scalars. So saying that if you take the commutator of any two x's, you get some linear combination of the xj's. Now, if you use the same Weyne-Norman intuition, your solution can be written as a product of exponentials, e to the c1 x1 dot 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 cn xn. And then you solve for these coefficients cn, and then you have your state u of t. And then with this, you can compute d theta u theta times u dagger. So this is how this problem is solved using the Weyne-Norman expansion. And firstly, how do you find these Cj? You literally write this u as an ansatz and substitute it into the equation of motion. You have a lot of everything expands with the product rule, and you just equate coefficients on each side, and you get differential equations for these C's, which is the nice thing about the Weyne-Norman expansion. You take what is an operator equation up here, and when you substitute this in, you're turning an operator equation into a scalar differential equation. So you do this, and then you just differentiate u to find v. But what are the problems with the Weyne-Norman expansion? Because I tried playing around with it. One is they are non-linear, because fundamentally, if you imagine what you're doing these three different rotations to end up here. It's not a linear thing. They have singularities because of this intuition about Euler angles from before. And lastly, they're difficult to interpret. Like, let's say you do find these scalar coefficients, C1, C2, and C3 of time. It's still hard to look at them and figure out what exactly they mean, because what you've got is a product of exponentials. If C1 changes by a bit, trying to visualize how that propagates through these products of operator exponentials and figure out how that affects the final state, that's not very easy. But instead, let's look at this V that we are computing. V is in the Lie algebra, and V is the thing we're looking for. Like if you're computing quantum Fisher information, you're not really trying to find U, you're trying to find V. So why don't we just parameterize V directly? One is it'll save us work. We don't need to find U and then differentiate U and then do this huge product here. But secondly, the tangent space is linear. So maybe our equations of motion here will actually be linear rather than nonlinear. So this is what we did. This is that paper with me and Jason. And we found, I've highlighted here the two equations that we've got, which is V, you can actually find a direct equation of motion for it right here. So dv by dt is the commutator of your Hamiltonian with V plus I partial theta h. And your initial condition is V at time 0 is equal to 0. So you just plug it into this equation of motion, and you can solve for V as a function of t. And you know that V can be written in terms of these operators in your Hamiltonian as a linear combination of operators in your Hamiltonian. So if we expand this top equation into components, we just get this. But the point is, well, these are linear differential equations rather than nonlinear. Lastly, if the Hamiltonian does not depend on time, you can write down an analytic solution, but you can look at the paper for more details. But the point of the matter is, here we have linear differential equations that we can use to study the quantum Fisher information. Like almost for free, we've turned a nonlinear problem into a linear problem just by thinking about this geometric intuition. So we consider this problem here. We have this long Hamiltonian here, but what it represents is we have uh, optomechanical system. So we have some kind of mirror which is moving up and down, interacting with a light field, and we have a gravitational signal that comes and affects it, that gives it a tug. So this is kind of simple model for LIGO, because LIGO, the giant 3 kilometer huge laser interferometry gravitational wave observatory used to detect gravitational waves, it uses suspended mirrors on pendulums and that are have light trapped between them. And then you model how does the cavity light output signal change when these gravitational signals move through. So this is a simple Hamiltonian that models this. And using the algebra techniques, you can, one, solve for your x as a function of t, and two is we can find an explicit equation for our quantum Fisher information, for our v. Now, when you look at this, right, the variance of v is what gives us our quantum Fisher information. And just looking at this equation here, we can tell what you want is the variant, your state to have high variance of, for example, either photon number or position or momentum. We have an explicit, nice formula here for the quantum Fisher information, which is very interpretable. And so what are the things we can learn from this? One, the quantum Fisher information depends only on the frequency of the gravitational wave, not its amplitude. Two, if you Taylor expand this, you can see, or if you set, if our gravitational wave omega g has the same frequency as our spring that the mirror is on, the quantum Fisher information grows quadratically with time. But the point of all this is we have an explicit formula for the quantum Fisher information, not going the long way through calculating u. And when you look at this, it is immediately interpretable. And we've got the details of this calculation in our paper. So to summarize this project, we can use ideas from Lie algebras and quantum dynamics to solve problems in quantum sensing. And we found Lie algebra parameterizations that were easier to interpret, that were linear, even for nonlinear dynamics, and they were singularity free, so better for numerical simulation. What I think is really nice is if you have a look at this paper, none of the maths we do is too complicated. It's basically all linear algebra. But what happens is it was just this viewpoint, like using this idea of geometry, of how these systems, what their mathematical structure is, it gave us the idea to then solve this problem. But then once you know how to look at it, once you know just make this ansatz for v and substitute it in, the actual maths is quite simple. It's just make this ansatz for our v, substitute it into the equations of motion, and find equations for these coefficients, v1 through to vn. So it's a really nice example of how knowing this kind of abstract or geometry maths can help you to solve real problems that people care about. So lastly, I'll talk about this thing, Lagrangian mechanics, and why I call what we're about to do real Lagrangian mechanics. Newtonian mechanics privileges Cartesian coordinates. It's not that you can't do Newtonian mechanics in terms of, for example, spherical coordinates, but it was built for X, Y, and Z. But then later on, you discover this thing called Lagrangian mechanics. Suppose you have a pendulum here. It's got mass m, angle theta, gravity g, and we want to study the motion of this pendulum. If you're using Newtonian mechanics, you'd need to give it an x coordinate, a y coordinate, and then encode this constraint somehow. But what you learn when you go to first year physics is you can pick whatever coordinates you want. You can say, hey, I want to describe this pendulum with angle theta, where theta is the angle this pendulum makes with the z-axis. And then you write down a Lagrangian. You have your kinetic energy term, half mv squared, and you have your gravitational term, and you stick it into these things called the Euler-Lagrange equations, and you get a nice equation of motion in terms of theta. So Lagrangian mechanics, it's very freeing. It pulls you away from this Cartesian way. You can work in Cartesian coordinates, or you can work in whatever coordinates that you like. And it's very nice. But we'll still find that this kind of Lagrangian mechanics that you are taught in first year uni still limits us, because while it's not using Cartesian coordinates, this is built on Euclidean space, and you can't directly apply this to non-Euclidean spaces. So what we'll see now in this part of the talk is how can you do truly general Lagrangian mechanics that you can apply to any system that you want in non-Euclidean coordinates. So as an example, we'll go back to this rigid body. So we saw you have a pendulum, and you can describe its orientation with three angles, and you can write down a Lagrangian and find equations of motion like this. And these coordinates had singularities. So previously, we built equations of motion using rotation matrices. But now we're going to do it a bit different. We're going to use these things called quaternions. And what I'm going to show is, firstly, what are quaternions? And then two, how can you say, I want to do Lagrangian mechanics using quaternions? And then how you can kind of build this theory. Now, I hope is it'll be general, how you can then apply this to kind of any coordinates you want. So firstly, let's have a quick crash course in quaternions. What are complex numbers? Well, we take the real numbers and we add an extra number I, and we say that I squared is equal to -1. What are quaternions? We add three numbers, I, j, k. We say that not only I squared is -1, j squared and k squared are also -1. And lastly, we have this relation here. ij is k, jk is I, ki is j. So if you take the product of any two, you get the other one. But the difference here is quaternions do not commute. ij is k, but ji is -k. And the way to kind of visualize this is you have this circle or triangle. If you're going along the arrow, ij is k. If you go backwards, ji is -k. So you have this kind of circular symmetry here. Now, as an aside, when you were in high school, when you learned 3D geometry, you might have seen people using these vectors I, j, and k to represent the coordinate axes x, y, and z. And so why is this? The reason is actually that, so initially, people discovered the complex numbers, and they found that you could use complex numbers to do 2D geometry. And this is very useful. But people wanted to do 3D geometry. And so they tried to move from the complex numbers. They thought, can we invent something new that will let us do 3D geometry? So initially, they were like, complex numbers have I. Why don't we add one more number like k? Sorry, like j. And then with these two numbers, can we do 3D geometry? They tried very hard, and it didn't work until eventually what a guy called Hamilton figured out is a complex number is a pair of real numbers. So if we want to go to the next stage, what we need is a pair of complex numbers. So the next step up from complex numbers is not three-dimensional, it's four-dimensional. It's two complex numbers. And this was the quaternions. And using the quaternions, Hamilton was able to do 3D geometry. Because back then, all these things that we think of, like the cross product and the dot product, didn't exist. No one had figured them out. So instead, people did 3D geometry with the quaternions. And it was only later when I think it was Heaviside, who was a mathematician, kind of thought, I don't like these quaternions. I don't want to learn quaternions. People shouldn't have to do them. And so he invented things like the cross product and the dot product that let us do geometry without the quaternions. But initially, people approach 3D problems using quaternions, using I, j, and k. And that's why we still use those letters today to represent the coordinate axes. So let's do a quick example of quaternion multiplication. Let's say we have this 1 plus I plus 2k times k. And you just multiply it out. K times 1 is k times I is ik, k times k is k squared. And then k squared is -1, ik. We're moving backwards along this triangle, so it'll be -j. And if we go the other way, k times 1 is k times I is ki, k times k is k squared, and now ki is moving along the arrow, so we get plus j. So you can see here that the quaternion product is not commutative. This times k is different to k times that. So for complex numbers, we have the conjugate. The conjugate of a plus bi is a minus bi. And for quaternions, it's just I, j, and k all become negative when you take the conjugate. Now, alpha we call the real part, and this part here we call the pure part, the pure quaternion part, the part that doesn't have a real number. For complex numbers, we have the norm. Alpha plus beta I squared is this product here, this times its conjugate. And if you expand this and use the rules of complex numbers, you get a squared plus b squared. For quaternions, it's exactly the same. The norm is a number times its conjugate. And if you expand all this and use all the rules, you'll find it's a squared plus b squared plus gamma squared plus delta squared. And we say that Q is a unit quaternion if Q star Q is equal to 1. Now, even Euler's formula. So for example, if you have e to the I theta, this is cos theta plus I sine theta. Now, if we have a quaternion Q, where Q squared is equal to -1, here I squared is equal to -1, e to the Q theta is cos theta plus Q sine theta. And the proof of these are exactly the same. You expand the left-hand side in a power series, use the fact that I or Q squared is -1, and you find that this decomposes into the power series of cos and sine. So some examples, for example, Q could be J, or Q could be K, or Q could be I plus J on square root 2. Now, let's say you have some vector, Wx, Wy, Wz. How do we represent this vector as a quaternion? We'd represent it as Wxi, Wyj, Wzk. So vectors can be represented as pure quaternions without a real part. We just map its components to ij and k. And then if you have two vectors, you can show that this product, Wv minus Vw as quaternions, corresponds to the cross product. I mean by that is if you take the cross product and take the components of this, the ij and k components will be equal to this quaternion product on the left. And again, you just show that by expanding both sides. So now, how do we represent orientation with a quaternion? Let's consider a particular orientation of our spherical pendulum. We can represent a general orientation. Any orientation of the pendulum can be seen as a rotation of angle theta about axis u. So any kind of orientation of the pendulum, you can say, hey, here's an axis u, here's an angle theta, and if you rotate about that axis by that angle, you will go there. So we basically only need 4 coordinates to describe an orientation: the x, y, and z components of the axis and the angle. And we can package these into a unit quaternion like so. The real part is cos theta on 2, and the quaternion part is sine theta on 2 times uxi plus uyj plus uzk. And you can show that q star q is 1 and q is a unit quaternion. So why do we do this? Let's say we have some vector, wx, wy, wz. Now, if you evaluate what is q, w, q star, you will find that the result is a pure quaternion, and the components of this are your original vector rotated by angle theta about u. So if you have a quaternion like this really does represent a rotation. You can use this q to represent any kind of rotation. So what we've done is we have chosen to represent the orientation of a rigid body as cos theta on 2, sine theta on 2u. This is simply a choice of coordinates. This is us as the human saying, hey, I want to describe my rigid body this way. Now let's see what this implies. We have position, now we need velocity. So if this is q of t, what is the velocity? Now we know that q star q is 1, and if we differentiate both sides of that, we find that v star q plus q star v is equal to 0. So this tells us that our velocity is a quaternion that satisfies this relation here for all times. So if I have a tangent vector at q, it must satisfy this relation here. It cannot be an arbitrary quaternion. It's a quaternion that satisfies these constraints. Because remember, your tangent vector v has to keep you a unit quaternion. It can't pull you off the unit sphere. And that's why we have this restriction that v is not arbitrary. But what does this mean? Let me define omega equal to 2q star v. So this factor of 2 is just me coming from the future saying, hey, you want a factor of 2 here. But you could just look at this. You could say q star v, let's call this omega. Then this equation here is saying omega plus omega star is equal to 0. Now remember, star is the conjugate. It leaves the real part untouched, and it sends the pure quaternion parts to minus. So if omega plus omega star is equal to 0, or in other words, omega star is equal to minus omega, this means the real part has to be 0. This is telling us that omega, this product of q star and v, has to be a pure quaternion. And in fact, omega turns out to be the angular velocity in the body frame. How can we show this? So we've shown that omega is a pure quaternion. What does it mean? Now let's let R here is a vector in the body frame. So I mean is, let's say I have a pendulum. So R here, even though I used R before for rotation matrices, now this is just a vector representing, for example, the vector pointing along the axis of my pendulum. Then if I have some orientation Q, we showed earlier that QR star represents the rotated orientation, right? You start off here, Q star gives you a rotated orientation. Then if you just differentiate this, R dot is, you use the product rule here. R is a constant vector representing the initial orientation. And then you expand. Here you have omega in terms of Q dot. You can solve for Q dot in terms of omega. And if you substitute this in, what you notice is that R dot is little omega R minus R times little omega. But this thing here we said is the cross product. So the point is, if I have a vector, my equation of motion for this vector is R dot is omega cross R. Now, if you know Euler's equations for rigid body motion, this is Euler's equation. This is how Euler says rigid bodies evolve, where omega is the angular velocity as seen by an observer in the lab frame. But so omega is my angular velocity in the lab frame. And this Q star is the rotation, which means big omega has to be my angular velocity in the body frame. So if my rigid body is rotating it around, omega says if you were sitting on the rigid body, what axis would you say that this is rotating about? So just to journey so far, we chose coordinates q like this, and we showed that if you have your velocity q dot, omega is your angular velocity in the body frame. Now q here has some meaning to us, right? It's a rotation. Omega has meaning to us. Q dot, it kind of doesn't directly have meaning. It's kind of weird thing, the derivative of the quaternion. So Q is our position. Let's choose to use omega as our velocity and not Q dot. And can we do that? And the answer is yes. For example, normally in equations of motion, maybe you think you have x and you have x dot, but that's not always true. Sometimes you use position and momentum in your equations of motion, like in Hamiltonian mechanics. You have x, and instead of x dot, you have the momentum corresponding to x. You can choose what you use to represent your velocity as. And because omega has a very nice meaning, the angular velocity in the body frame, let's choose to let omega be our equations of motion to contain q and omega. So now let's look at how we can find Lagrangian equations. So you start with a Lagrangian, right? Let's go through the classical derivation of Lagrangian equations. So no quaternions, nothing, just with real numbers. So for example, back to the pendulum. So here Q isn't a quaternion, Q is any coordinate on our system. Q could be the angle of that pendulum we were talking about earlier. How do people derive Euler-Lagrange equations? Well, they say this is my action, and my trajectory is a point of stationary action. So what this means is if my q goes to q plus delta q, my action should stay the same. So if q goes to q plus delta q is the variation in my position, delta q dot is the variation in my velocity here. And so delta s is dl by dq delta q, dl by q dot delta q dot, and then you use integration by parts to move this derivative to here, and you end up with this. And then you say delta q was arbitrary, so for this to equal to 0, this quantity in brackets must equal to 0. And then that gives us our Euler-Lagrange equations. Now, can we apply this to the quaternions? The answer is no, because this derivation assumes Euclidean space. What do I mean by that? Here, you take q and you add an arbitrary variation to it, because the whole point here is this derivation only works if delta q is completely arbitrary. We say delta q can be anything, so the only way for this to be 0 is if this inside here is 0. But in the quaternion case, you can't just take a unit quaternion, add anything to it, and stay a unit quaternion. If you're on the unit sphere, you can only add vectors that are perpendicular to it. If you add any vector with a parallel component, you're no longer on the sphere. It's only in Euclidean space that you can add an arbitrary variation to your object and stay inside your configuration space. So our derivation fails because we end up here. This is all very well and good, but delta Q is not arbitrary. It can only take some specific values. And because delta Q isn't arbitrary, we cannot conclude that this is zero, only that this is kind of orthogonal to delta Q. So what can we do? How can we generalize Euler-Lagrange equations to any non-Euclidean space? We need more freedom. We need a geometric framework that works beyond Euclidean space. And so I recommend, if you want to learn this, there are a few books, but this is the one that I learned it from. It's quite good. It's called Global Formulations for Lagrangian and Hamiltonian Dynamics on Manifolds. You'll find a geometric framework and there that shows you how to generalize Euler-Lagrange equations to general spaces. So let eta now be an arbitrary pure quaternion. So it's got an x, y, and a z component. Now fix some epsilon, which is a scalar, and define q epsilon to be this. So q times e to the epsilon eta. Now if q is a unit quaternion, q star is 1, because what is q star? Q star is e to the, maybe I should actually draw this. If you take the star of this, you'll have e to the minus eta epsilon. I can't actually draw it because I'm on my thing, but if you star this thing here, your eta becomes minus eta because I, j, and k become minus eta. And then q star will be 1 because this e to the epsilon eta and e to the minus epsilon eta will cancel out. So now let's say this is my variation in q. I haven't added something arbitrary to it. I've multiplied it by e to the epsilon eta, where eta is arbitrary. How can I find the infinitesimal variation in q? It's d by d epsilon q epsilon, evaluated at epsilon equal to 0, and that gives me q eta. So okay, this is my variation in position. What about my variation in omega? Well, again, I substitute this thing here into q star and then into q dot. If you differentiate this, you'll have the product rule. You'll have two terms. And then you differentiate d by d omega at epsilon equal d by d epsilon of omega at epsilon equal to 0. And you get this thing here for your variation to your velocity. So in Euclidean space, we have this for delta q arbitrary. For us, delta q is not arbitrary, but we can write delta q in terms of eta, where eta is arbitrary. So what do? We basically have our L, and just like before, we expand dl by dq, dl by dq star, dl by omega here. And then we substitute delta q as q eta. Delta q star is the conjugate of this. When you take the conjugate, you swap the order and get a minus sign. And here you have omega. And we basically want to massage this until it is something times eta. And if you do all that, then the thing that's over here has to be 0. And if you do all that, you get your Euler-Lagrange equations in the quaternions. So here we have q dot is a half q omega. This was just our earlier definition of omega. But this here is our Euler-Lagrange equation. And this, I think it's new. If anyone has seen this equation before, please let me know. But I think this is something that we have derived. And if you look in the geometric framework, this is a special case of something called the Euler-Poincaré equations. But if we want to summarize what we did, we said, okay, we are going to choose to represent the orientation of a rigid body as a quaternion, a unit quaternion. And then if I want to know the evolution of some vector on my rigid body, this is how it evolves. R of t equals qr star. And this just comes from, you can just show that if you do this product, you do get the rotated R. And then just using the fact that q star q is equal to 1, we found that we must have this quantity omega as a pure quaternion. And then substituting this into this equation here, we find that omega is the angular velocity in the body frame. And then this thing here is just can be restated as this. Now, we want to describe variations in Q. We find that we can do this like this. And we ended up with our variations here. And when we substituted this into the Euler-Lagrange equations, we got this. So this is like the general framework. You can see how to do it here. And this can let you do, for example, you could do this exact same thing with the rotation matrices. And then you would have Euler-Lagrange equations in terms of the rotation matrices. And as an example of this, let's say you have a free rigid body. It has just kinetic energy, no external potential. These are equations for Q, these are your equations for omega. So your quaternion equations are here, and you notice that they are linear. If you had equations for Euler angles, they would be nonlinear. These are linear. And then your equations of motion for your angular velocity are the same as the Euler's equations. Now, these quaternion equations, by the way, aren't new. Other people have derived them. What we think is new is this general framework where you can just write down a Lagrangian and get equations of motion. But the point is that this is what these equations look like, and they are nice and linear, so you don't have singularities like with Euler's equations. Um, Singularity quaternion equations. And as an example, we considered something called the tennis racket theorem or intermediate axis theorem, which is if you have an object which has three different moments of inertia, one big, one medium, one small, if you rotate it around the intermediate axis, the axis whose moment of inertia is in between the other two axes, it'll be unstable. So here's an example aboard the International Space Station. They spin this, and this middle axis is unstable. It just keeps flipping. And we simulated this here. And if you start off rotating it around by either of the big or small axes, it'll just rotate stably. But if you rotate around the intermediate axis, it'll flip. So that kind of shows that these equations do work. So in conclusion, classical and quantum systems have dynamics described by non-Euclidean spaces. A lot of what we do is shoehorning these into Euclidean space, but this comes with consequences. But if you can understand geometry, this somewhat abstract mathematics, which seems, very kind of high and removed from practice, can in fact really simplify computations and problems, very down-to-earth problems that we're solving. So again, this is my work. These are my collaborators. These are links to the paper. Thank you very much for listening and your attention.
That's fantastic. Thank you so much, Ruvi. That was a fantastic talk.
Yeah, thanks, Derek, for having me. It was a pleasure.
It's a pleasure.